Hello, everyone. Thank you very much for joining our lunchtime webinar on the European Laboratory for Structural Assessment of the Joint Research Center. I am Maria Liapopoulou. I am the chair of the second Young Member Subcommittee. And we have with us today Georgios Tsionis, Marco Lamperti Tornaghi, and Marco Peroni from the JRC. I would like to please ask the audience to keep your video cameras off and your microphones on mute for the durations of the presentations. This applies only to the audience, so please, I would ask the speakers to keep your video cameras on during the presentations. There will be a question and answer session at the end. So please feel free to type any questions you may have in the meantime in the chat, and these will be answered after the end of the presentations. And also please note that the seminar is recorded and will be uploaded on our second YouTube channel. So by dialing into this event, you agree that any information or views you share will be made public. Before we begin, I would like to make a couple of announcements from SECET. On the 28th of May, we have the Mallet-Milne lecture. This is a biennial event established by SECET in honor of the pioneering British scientists Robert Mallet and John Milne. And the 19th Mallet-Milne lecture will be delivered by Professor Calvi. The title of the lecture is Risk Management and Rehousing of People Displaced by Earthquake Disasters, and the publication accompanying the lecture is available online in the Bulletin of Earthquake Engineering. The lecture is free of charge. It will take place in the Godfrey Mitchell Theatre at the Institution of Civil Engineers and is kindly sponsored by Ramboll, Servotest, Atkins Realis, AWE Nuclear Security Technologies, and Jacobs. You do need to register if you want to attend the lecture, either in person or online. And for those of you attending in person, there will also be a drinks reception after the lecture, for which you can buy your ticket online when you do your registration. On the 13th of June, we will have a site visit to the Schofield Centre at the University of Cambridge. The Schofield Centre is a world-renowned lab for physical modeling in geotechnics and includes centrifuge testing facilities. The site visit will include a tour of the center and presentations by Professor Madabusi, the director of the Schofield Center, and researchers from the Geotechnical and Environmental Research Group of Cambridge. It is free of charge to attend the site visit. You need to be a member of SECET, either an individual SECET member or an employee of a corporate SECET member. If you are not yet a member, please consider applying for membership, and this is free of charge for students. Keep an eye on our website and LinkedIn for the announcement of the site visit. And please note that there will be only 20 places available, allocated on a first come, first served basis. So you do need to register if you want to attend that. Now back to our event. The seminar will be delivered by Dr. Georgios Tsionis, Marco Lamperti Tornaghi, and Dr. Marco Peroni. Dr. Tsionis is the deputy head of the unit Built Environment with expertise in seismic risk and resilience assessment, integrating socioeconomic and sustainability aspects. He has experience in the standardization in the built environment and has provided scientific advice to policymaking. Dr. Tsionis has been involved in numerous European research projects and Marie Curie actions in earthquake engineering, including large-scale experimental testing, numerical modeling, fragility analysis of reinforced concrete and precast concrete buildings, as well as post-earthquake field missions, and has co-authored more than 70 peer-reviewed articles. Marco Lamperti Tornaghi is laboratory technician at the ELSA reaction wall. and has experience in earthquake engineering research, including the seismic response of full-scale testing and connections, the integration of safety and sustainability, as well as innovative building materials. Marco has been involved in European research projects and post-earthquake missions and has co-authored more than 70 peer-reviewed articles. Marco also represents the JRC in the action implementation of circular economy in the built environment. Dr. Marco Peroni is responsible for the ELSA reaction wall and HOB lab laboratory activities, with experience in high strain rate mechanical testing, large-scale numerical and experimental testing, and the dynamic behavior of materials and structure, including impact and blast loading. Marco has a PhD degree in mechanical design and machine construction and is proficient in English and French. So without further delay, I will hand over to Georgios to start the presentation.
Thank you very much, Maria, for the kind introduction and most of all for giving us the opportunity to present to SECED, the European Laboratory for Structural Assessment of the Joint Research Center. And I would also like to thank the participants to this webinar for your interest. In my presentation, I would like to start with some information about, very briefly, what the Joint Research Center is. Then I will give you more information about the reaction wall and some examples of recent projects and information about opportunities for collaboration, and then hand over to my colleagues for more details on specific project at the reaction wall, and then details on the HOP Lab facility. So the Joint Research Center is a Directorate General of the European Commission, and our purpose is to provide independent, evidence-based knowledge and science, and we are supporting EU policies all across areas and the whole cycle of policy making, ultimately with the objective to have a positive impact on society. The Joint Research Center, or JRC in short, has the headquarters in Brussels, and then research facilities located in Belgium, Germany, Italy, the Netherlands, and Spain. The European Laboratory for Structural Assessment is based in Ispra in the north of Italy. The Joint Research Center is organized in a number of directorates and then units. Our unit that operates ELSA is called Built Environment, and we deal with the residents of the built environment. As you know very well, the built environment is vulnerable to natural disasters, including the effects of climate change. On the screen, you can see some examples of earthquakes that you are probably mostly interested in, but also fires and all the impacts of climate change. Recently, we started looking at the issues related to the aging transport infrastructure. You can see that in Europe, this is like the backbone of all the countries, and with a significant impact in case of disruption. And recently also some interest about military mobility through the transport infrastructure. We are very keen to transfer all the knowledge we produce to European standards, for example, the Eurocodes. They are a very good tool to address all these issues of resilience of the built environment and also support very much the competitiveness of the European construction sector in the European single market and also abroad. And recently, as you are very well aware, we started dealing with issues related to sustainability. For example, the use of critical raw materials in construction, which is quite a concern. And we will be looking also at solutions about how these critical raw materials may be replaced by advanced materials. Coming now to the European Laboratory for Structural Assessment, or ELSA in short, it actually comprises two laboratories, HOPLab and the reaction wall. We use these to support our activities related to the resilience of the built environment, and we operate the two facilities under Horizon Europe projects within the program for opening access to JRC research infrastructures for research and for training. I will tell you more in the following. We use it also for internal projects of the Joint Research Center, like proof of concept or exploratory research. And we constantly look at improving and maintaining the research infrastructures and the database of experimental results. The reaction wall is used for the safety assessment of structures against natural and man-made hazards. It is the largest one of this kind in Europe and one of the 2 or 3 largest ones in the world. Imagine, as you can see also in some images later on, that we can test a full-scale building of up to 4 stories high in both horizontal directions. For the case of larger structures, for example, bridges that do not physically fit inside the space of the laboratory, we can apply a hybrid testing method where we test a physical part of the structure, let's say the bridge piers, where we expect to have damage and non-linear behavior, combined with a numerical model of the rest of the structure, for example, other piers or the deck, for which we are confident about our numerical models. And all this is, all the two parts communicate in real time, and we are able to test a full structure. This is an example of the lifetime of a testing program. We normally construct our specimens outside of the lab, and as you see on the screen, slowly move them inside the lab and place them in front of the reaction wall, using a set of horizontal actuators attached on the wall, and then at the floors of the specimen, we apply the displacements that would normally be produced during an earthquake. We do this quite slowly. This video is accelerated, and whereas an earthquake may last 15 or 20 seconds, a test in our laboratory can last a few hours. This allows us to follow closely all the details of how the damage evolves in the different places of our structure. In the end, we transport the specimen outside of our facility. You can see here a bird's eye view. We demolish the specimens and separate the materials. And this is a very good opportunity to study how we may reuse the materials in new construction, and in this way have a better, a lower environmental impact of new construction and improve circularity in our buildings. Another example of a recent project, not actually related to earthquake engineering, but a good example, I believe, of a disruptive technology related to aging tunnels in Europe. The idea is actually a machine that can use to repair old tunnels, old reinforced concrete tunnels. This technology can be up to 10 times faster than conventional technologies. It can extend the lifetime of a tunnel to 100 years, and this uses fiber-reinforced concrete. As you can see, a slice of the new tunnel lining on the other picture. With good economy and low use of materials. How did the test look like? This is a slice of the tunnel, and using this set of horizontal actuators, we were able to apply large forces with different patterns originating from the soil above the tunnel. With the naked eye, we cannot see much on the specimen, but through our instruments, we can measure, for example, the deformation here in magnified mode. And through digital image correlation, we can also monitor the evolution of damage and very well the opening of the crack in this area of the specimen. Another example of recent project is a building made of timber panels. These are modules that can be used in different configurations. Timber, as you know, has very good environmental performance, very good performance in terms of energy efficiency. This small building was constructed actually during 2 days. This is the first configuration that you see on the screen. After a series of tests, a different configuration was implemented using the same elements and then tested again. This is a test of a video of one of the seismic tests on this structure. What is innovative is the kind of a new kind of connections between the timber panels that you can see on this side of the screen. These are designed by our colleagues at the Joint Research Center. They are designed to dissipate all the energy during the earthquake. And then if there is some damage, only this small metallic part can be changed, which is very fast and cheap. And after very strong earthquakes, during our tests, it was shown that the timber panels had no damage and only some of these sacrificial elements had to be changed, and then the structure was as good as new. Overall, we have a history of more than 30 years of collaborative projects. We have contributed together with our partners, of course, to improving knowledge on seismic safety, transferring this knowledge to European and international standards, supporting transnational access and training and mobility of young researchers. And of course, this was also helpful to improving the operation of ELSA with good quality, safety, and sharing our data. We share our data through a data access portal that has been developed within the IRIS project of the Horizon Europe program. And you can find the data from the JRC and from all the other partners of the project on this portal. All the data are available to download and to be used as you wish. And by data, I mean not only the experimental data, but also information about the projects. Now, for a few more days, there is a call for applications for scientific trainees at the Joint Research Center. I will share afterwards on the chat the link. JRC may participate in Horizon Europe programs when mentioned in the work program as beneficiary requested zero funding or associated partner, and can also be an associated partner in Marie Curie actions. JRC can also host unpaid visiting scientists for a period of 1 to 12 months after an agreement is signed between JRC and the sending party. And as the name says, there is no financial compensation in this case from the JRC. Lastly, now there is a call for proposals for access to JRC research infrastructures. Hope Lab with a number of research topics related to security, circular materials, additive manufacturing processes, new components under blast and impact, and for the reaction wall, also for a number of topics related to renovation of buildings, design for resilience, sustainable materials, and testing methods. These projects are for performing research at the two facilities. You may find more information on the links that I'm sharing on the screen and will share afterwards also on the chat. And you are, if you have any idea for projects, please feel free to contact us. I would like to let you know also about the blind prediction competition organized under a project of series related to the evaluation of masonry vaults under seismic actions. And there will be a special session at the next conference on structural analysis of historical construction. And with this, I thank you very much for your attention. I'm sharing the links to the two facilities and our email if you would like to contact us. Thank you very much for your attention.
Great. Yes. Thank you very much. And we can see the screen, Marco. So that's good.
Thank you, Maria, for the presentation. I would like to bring you closer to an experimental project like the slab stress. Slab stress was presented during the previous presentation of Georgios, and sorry, but okay. It was a transnational access in the SERA-TA program, who had the joint collaboration of four research group: Politecnico di Milano, École Polytechnique de Lausanne, Nova University of Lisbon, and the Technical University of Bucharest. And the main object of this project was to test the seismic during the earthquake, a flat slab building. This is the layout of the mock-up. It was a full-scale building for 2 floors, almost 14-meter long and 10-meter large. Was designed according to the Eurocode 2 because as you know, in the Eurocode 8, there is a statement that excludes explicitly the flat slab building for earthquake use in earthquake area. Thanks to the research and thanks to the project Slabstress, the new version of the Eurocode 8 will include also the flat slab building for low and medium seismicity area. So the layout was designed according to the Eurocode 2, using two different layouts for the reinforcement. One using concentrated or horizontal reinforcement close to the columns, and the other using a smeared reinforcement. And the two stories, the two floors, were differently reinforced for the punching reinforcement. So the second story had the punching reinforcement, while the first not. The design of this so complicated mock-up required different internal cooperation. First, we need to know all the internal action into the column to slab connection. This was not possible to measure inside the interface between the column and the slab. So we decide to measure the forces and the action. The internal action means bending moment, shear load, and axial load into the column to reconstruct the stress behavior into the slab column connection. And then we need to connect the actuator with the so thin slab, and using an unusual application of horizontal load compared to our experience in the lab. And finally, we need to integrate also the safety measures to avoid catastrophic failure. That is this propping for the first load and the capitals mounted on the second story to avoid the failure of the slab in case of generalized punching. Here you can see the integration of this device, which are load cells, into the reinforcement of the column. This allows us to measure the behavior of the column during the test. You already seen this image in the Georgios presentation, so I skip this to the next one, just to give you also the magnitude of the instruments we employed. We use 80 inclinometers to measure both the inclination of the column and of the slab, 24 transducers for internal action, bending moment, shear, and axial load, and 48 linear displacement transducer to measure the cracking within the slab. All this data gives around 200 data acquisition signals that are synchronized together with the actuators using to stress the building during the test. That gives also the displacement of the actuator during the test and the load measured by the load cell mounted directly on the actuator. This allows us also to check the goodness of the measuring of the shear load by the internal instruments, because the difference between the load measured by external actuator and internal transducer was had only the 4% of difference of error between the two measures. Here you have a closer look for these load cells, but that was designed on purpose. The location of inclinometers on the slab and the location of inclinometer on the column, and the vertical displacement transducer to measure the crack within the slab, because as you know, the crack is inclined within the slab, starting from the bottom part of the column and propagating in this way. Using this vertical transducer within the slab, we were also able to measure the cracking of this part. So you see that we had three kind of column: the central one, the corner one, and the edge one, and this required to have a different setup for inclinometer, for crack opening displacement transducer, and for load cell. Each of them specialized for each kind of connection, each kind of connection between the column and the slab. Before the testing, the real scale testing, we calibrated all the instruments and all the measurement chain of instruments. This required to design an innovative calibration kit for the load cell. You see here a load cell alone tested with this system, and we are used to test also the inclinometers and the crack opening displacement transducer before the test. Here you can see the evaluation on this. This was also interesting because during the final test, we are completely concentrated on the full-scale test, and the whole measuring chain calibrated ex ante at 0 killed during the final phase of the test. We had a problem in measuring axial load for the noise generated by the bending behavior of the column, and we haven't time to solve this, but now we developed during this year a second generation of the load cell able to solve also this problem. This is the setup of the vertical loads, while horizontal loads are applied by the actuators. We use the water tanks for the first floor and concrete blocks for the second. During the different tests, we had different pattern of gravity load distribution to simulate different conditions of using this slab. For the earthquake load, we used this ground motion from Bingöl, recorded in Bingöl, Turkey in 2003, scaled at 31.87% to simulate the service limit state and the ultimate limit state. And we use also cyclic load up to the 6% of the drift ratio for the whole building, both for the preliminary phase and for the final test. We use this one up to 60, more than 70%, while in the preliminary phase we keep the drift below 2.5%. Here you can see also the compatibility between the design spectra and the accelerogram we used. After a first phase of test, we simulated the earthquake on the full-scale building. We damaged some connection, and for 3 connections, B1, C2, and C3, we introduced the retrofitting after the cyclic test 1, using where the slab were not preliminary reinforced by internal reinforcement. We tested also slab without punching shear reinforcement, damaged by the earthquake, and retrofitted after the earthquake to assess the possibility of a strengthening on real existing building not designed for this purpose. This is a brief presentation of the test result. You see here the first cyclic test in orange and the second in blue. You can compare directly the central column unstrengthened, in this case the B2, and strengthened, the C2, and you see here a drop of the resistance caused by the punching, and then the second part of the earthquake that had a lower stiffness and resistance compared to the strengthened one that increase the stiffness, increase the resistance during the earthquake. So this is to demonstrate that the strengthening was efficient in increasing the resistance of building not designed for the earthquake area. Here you can see the test, the video of the test was already presented by Georgios, is accelerated. So in the first phase, you can see the displacement of the building, which is 6%, more than 6% of the drift, while here you have a close-up of the central column that captured the punching during the test. The punching in this sense was caused by the earthquake action and not just for the vertical action. It was a combination between gravity load and earthquake load. So going to the conclusion, the slab stress was the answer to several questions related to the use of flat slab buildings in earthquake-prone area. This required to design and develop new transducers for measuring internal action in the column, and to coordinate this big number of instruments together with the control system using a calibration technique and the calibration procedure we developed internally. The strengthening was effective in preventing the punching shear collapse, and all the experimental results are available for research community to bridge the gap between the whole building behavior and the local behavior of flat slab connection. As Georgios said before, you can download all the experimental data from the ARIS website. Here you have also 3 papers that could be used as references of this experimental project. You can follow the link and download this paper. This is the end of the slab stress project, and as Georgios said before, this is the starting point to start analyzing the reuse of material and to improve the recycling and reduce the amount of material used in the construction sector. Our capacity to be very fast in testing, demolishing, and construct is also a good opportunity to challenge ourselves to use new techniques to improve the circular economy of building. We are bound to start a new series of tests in the IRIS project. One of these is called Recycle Slab, is managed by a larger group compared to the former project, is coordinated by the University of Lisbon together with Polytechnic University of Madrid, Polytechnic di Milano, Imperial College of London, and the Slovak University of Technology in Bratislava. In this project, we are trying to reduce the amount of concrete used in flat slab by 20%, and the flat slab are made using 50% of recycling aggregate. This means to reduce the footprint of concrete by 40%. Thank you very much for your attention, and I hope you enjoyed this project, and you can find all the data in the link I left you. Thank you very much.
Thanks a lot, Marco, for the very interesting presentation. And we have the last presentation for today from Marco Peroni. So if you could share your screen as well.
Yes, okay. Okay, do you see my screen?
Great, yes.
Okay, perfect. As Georgios said, The second facility, main facility of the European Laboratory for Structural Assessment is called OPLAB. It's something a little bit, probably a little bit strange for civil application, because it historically is more devoted to mechanical testing. What is the difference comparing with the reaction wall is that the OPLA laboratory is more devoted to simulate very fast dynamic loads, like the one produced by blast and impacts in general. At OPLAB, there is, we run a lot of facilities that are normally called Hopkinson bar, and we had at OPLAB the largest Hopkinson bar of the world. That is very long because it's 200 meters, compared the classical 10 meter long of a conventional Hopkinson bar. And then we have also some other more conventional facility to test all, in general, all the material, all the structural material normally used in mechanics or in civil application. This is the diagram of the large facility that we have. This one that is 200 meter long, and okay, it's not so simple to understand for people that are not involved in high strain rate testing, but substantially the operating principle is quite simple, because there is a sort of elastic that is pre-stressed and fixed at one extremity with an explosive bolt. When you pull the cable and you quickly release it, these ends move very fast in one direction, and to these ends is connected a bar. In this way, you can produce a tensile pulse or a compression pulse that go to the specimen and apply a very rapid load to the specimen. And these are some images related to this facility. Some portion of the facility. You can see in the upper left photo the huge actuator that pulled the bar. You can see also on the bottom right the explosive bolt that fixed the rig at the first instant of the test, and you see that the bolt also, there is a bolt that has been already used, and you see that is broken by the explosive inserted in this small hole that you can see in the upper bolts. And on the upper right photo, you can see the test section of the machine. In practice, what we can do with this machine, we can apply very huge load up to 100 tons in less than 40 milliseconds. It means that with this machine, all the pieces move at a velocity of about 10 meters per second. That is totally another level compared to the reaction wall, where the maximum velocity that we can achieve is around 1/10 millimeter per second. And in this kind of experiment, we typically adopt high-speed imaging, because it's not possible to see nothing with your eye. And also the instrumentation is quite complex and dedicated, because we have to acquire measurement up to 1 to 10 megahertz. This is the video that you see at the bottom is the classical specimen for metallic material that we use, that has a cross-section, gauge cross-section up to 30 millimeter, and give to you the idea of our capability in terms of load and in terms of forces. Why this machine is useful? Because probably if you have to test material like conventional metal, it's not interesting to have a specimen so huge, because it's more cost efficiently to use what you can see here in the upper photo, the standard size of the specimen and the standard equipment. You see that our specimen for this machine is more than 10 times larger. But it is interesting to do tests on large scale specimen, because a lot of advanced material has a core structure, a structure that has elemental volume up to 2-3 millimeter, and it's not possible to do test on this material with conventional specimens that are long, maximum 2 or 3 centimeter, because the testing volume is no more representative. For this reason, this is the only facility in the world that can do tests on this kind of material. You can see here some example. This is a video of a composite test made with this machine, and the test lasts less than 1 millisecond. And you can see we tested also normally aluminum foams that has this kind of structure, also other type of composite like the one presented in the bottom right images that are related to composite for personal protection, like Kevlar composite normally used for bulletproof jacket or helmets. This is another machine quite large that we have the OPLAB laboratory. This machine was in compression, not in tension like the previous one, and is smaller in terms of size, but is larger in terms of maximum forces that we can apply. We can apply, in fact, with this machine up to 4 meganewton, 400 tons. Also in this case, in less than 1 millisecond. And typically, we use this machine for brittle material. We have a lot of requests for concrete or geometric material application, and also for more ductile material like foams and structure 3D printed. That is one of the trendy topic for energy absorption capabilities. I show you some video related some test performed on this machine. You can see here the specimen on the left, the specimen that is this cylinder up of 10 centimeter of diameter and 5 centimeter of length. This is a video at real velocity. You see in practically that the test lasts very few instants, and with your eyes it's not possible to see practically nothing. But on the right, you have an high-speed recording, and you can see that it is feasible also to apply digital image correlation or to track the movement of the machine during this kind of phenomena that lasts less than 1 millisecond, sorry. We have also at the OPLAB some more conventional machine that are smaller. This one, for example, is we have 2 setup for tension. This setup have this bar of 10 millimeter of diameter. It means that the specimen is small, and you can see in the photo is something with a gauge section of 3 millimeter. And also in this case, the test lasts very few milliseconds. We have also some machine for compression, like this one, and you can see some images related to a compression test made on a copper specimen. And the idea is always to perform tests very fast. Concerning OPLAB, and probably something that Georgios already mentioned, every year we organize a course related to the Hopkinson bar techniques, and we prepare this course of 4 days, where we try to explain the techniques from the basis to the state-of-the-art techniques. And in this course we had also 4 hands-on sessions on the different facilities that we have in our laboratory. Some tests that we did in the past with the machine are collected in this slide. You can see on the right the older specimen related to the nuclear research, because our JRC started as a nuclear research center, and for example, these specimens were directly cut by a nuclear vessel. On the left upper side, you can see some specimen related to compression test on automotive and train crash box or system to absorb energy. And these tests have been done mainly in the 90s probably. And the last test on the bottom are more related to the civil sector, and you can see some test specimen for compression or for some pull-out test made on reinforced concrete part. These are some quite recent tests related to the open access project that Georgios also mentioned. You can see that we tested, for example, some material for the CERN related to this electron beam welded specimen made of niobium and copper. We made a project also on automated tape composite in collaboration with York, Oxford and Edinburgh University. These are some composite with very large structure. We tested also some high strength and very high strength steel for civil application in collaboration with some university, some Switzerland university, and also we test in collaboration with Delft University and TNO mainly some specimen related to Adobe masonry applied to that are used in dynamic application. This last slide is related to the two very recent tests that we made always in the open access project schemes. You can see something quite trendy in terms of research on the left. This is a compression test on a structure 3D printed. This is known typically triple minimum surface structure, and you can see that it's feasible to test also this kind of material. The specimen in this case is something of 2-3 centimeters of side. On the right, you can see something a little bit different. Is a crash box, is an advanced crash box for for vehicle application. This is made with a 3D printed core in composite, and also the skin is carbon composite with an origami shapes to tailor exactly the energy capability of this component. And probably that's all from my side. And thank you. I stop sharing.
Great. Thank you very much all for your presentations. You gave us a very comprehensive overview of the activities and the testing facilities at JRC. I had the pleasure personally to see that last year during a visit at the Joint Research Center, but I think this gives a very good overview for the rest of the people. And thank you for sharing the opportunities for research as well and the traineeship programs. Now I would like to open the floor for questions from the audience. So if anyone has a question, please unmute yourselves and ask the question, or otherwise you can type in the chat. Mohammed, I can start with Mohammed.
Yes, hello. Thank you very much for the interesting presentation. I just had a question on the compression impact test in the Hopkinson machine. I saw that the specimen, the depth of it is about 5 centimeters, which is probably due to inertial effects. But how significant are those inertial effects if the depth is larger? Do the results change significantly if you've tested any specimens with larger depths?
Obviously, these kind of tests were developed mainly for small specimen. It means that typically in this context, inertia effect could be neglected. Obviously, increasing the size of the specimen, you could expect that inertia effect became more relevant. But we have to understand also that in this kind of test, the specimen remain in equilibrium. It means that the force at the left side is equal to the force of the right side at a certain point. Obviously not in the first instant of the test. And also increases in the size of the specimen, typically you go a little bit at lower velocity. It means that also in this case, also with the specimen up to 10 centimeter of size, you can neglect inertia phenomena. Obviously, you have always to, one good practice is always to simulate the test to understand if this is totally true. Because it depends also on the strength of the material. If you test material like soft human tissue, it's a problem because the strength is very low and inertia phenomena are relevant. If you test something like concrete that can reach also, because dynamically the strength can improve up to 3 times, these could be neglected. It depends. You have always to check the material that you are testing and things like this.
And how long is the incident bar in this test? Is it
in this test with brittle material? We are talking about 2-3 meters because also the material is very, very brittle. It failed very early. Also for the ductile test, we use a bar like this, but we modify a little bit the configuration to have very long pulses. In this way, we can deform. You saw the test of the crash box. We can have also deformation up to 6 centimeters. That is a huge stroke for a Hopkinson bar.
okay? And I have another question if nobody is asking. This was on the slab stress or stress slab test that was shown by Marco earlier. And I wondered if any of the results had any influence on the Eurocode 8, for example, recommendations for reinforcement for flat slabs or...
Georgios, could you answer because it's more your topics?
Yes, thank you. This would be probably Marco Lamperti could give a better answer than me. There wasn't actually a direct input to Eurocode 8 because you may not know, but there is an ongoing revision of all the Eurocodes, and the time when the results were available, the works for revision of this part were over, and it was not possible to include any other information. However, this has been communicated to the technical committee, and there was also, based on some of these results, an update of punching shear design rules in the FIB model code.
Thank you very much.
Great. I also see a question by Ashraf in the chat. Ashraf, would you like to unmute yourself and ask the question, or otherwise I can just read from the chat? Yeah, so the question is, one of the reasons for the use of smaller specimens is to reduce the inertia effect. And then if one of the Hopkinson bars can be readapted to test other types of loading, for example, the tension bar to apply compression and vice versa.
Yes, typically it's feasible to do this kind of things. Obviously, it depends always from the specimen that you have to work. It means that in this kind of experiment, there is no a unique facility for all the type of material. You have always to adapt in terms of size of the bar and material of the bar, your facility to your specimen. But it's feasible to do testing compression with some tricks using a tension machine and vice versa. It's something that we did also in the past. The problem is that when you do something like this, you add some masses that can affect your data. It means that more simple is the design of the test, more effective you are to measure something that is reliable.
Great. Okay, perfect. I think now we are over with the time. So thank you very much for your presentations, and thanks everyone for attending.